Okay, this was the second half of the lesson that we covered last time, simplifying radicals. Now, for the most part, we got through all of it, but I know we were rushed in some areas, so I want to go over it again. That way you have the notes and the recording. Let's get started. So whenever you are doing radicals, first off, you got to remember that the radical expression contains a radical or a square root symbol. Okay? The expression under the radical is called the radicand. You should have that from the first half of the notes or the last video. As a reminder, the radicand, to give you a visual, would be anything under the radical. Okay? All of this stuff is under the radical, therefore all of it is the radicand. Now, in order for it to be in its simplest form, there have to be three conditions. There are three conditions that must be true. The radicands cannot have perfect squares underneath them, which means if I were to have the square root of 12, if I were to do a quick tree off to the side, 12 contains 4, and 4 is a perfect square. I would have to take the square root of 4 and simplify it all the way down and get to root 3 in order for it to be completely simplified. Next, radicands cannot contain fractions. So we've done examples like this in class, okay, where we had a fraction under the radical. Whenever this happens, you're going to take the square root of the numerator and the square root of the denominator in order to simplify it completely. Now, to clarify, you can have the radical as a part of a fraction. So if I go over here, the square root of 3 over 2, that's fine. That works. You just can't have the entire fraction within the radical. Okay, and this example goes up here. Now, last but not least, radicals cannot appear in the denominator. So I just said radicals can be in the numerator. That's correct. That is fine. However, what you could not have, and I'll write it in red so you can see that you can't have it, would be 3 over the square root of 2. All right, you would have to somehow get the square root of 2 out of your denominator in order for it to be completely simplified. Now, the product property of square roots basically says that if I have any number under a radical, I can spread out its factors. Okay, and I showed you this in class, but I'll do it again. If we have the square root of AB, that would be the exact same thing as the square root of A times the square root of B. Now, yes, it's written down here as well. If you want to write that one, that's fine. Another example would be if I have the square root of 12, I could spread this out to the square root of 4 times the square root of 3. This is useful because now I can see the square root of 4. I know the square root of 4 is 2. There is no square root of 3, so it just comes down. And then this would be your answer. Now, this property works both ways. Let's say I had the square root of 3 times the square root of 5. Okay, that would simplify into the square root of 15. So the product property of square roots both separates the factors so that you can more easily see your perfect squares, and it combines them. But please notice it has to be multiplication. So some practice. Take this first one. I have the square root of 5 times the square root of 10. If I break down the square root of 10, I get this. Okay, all I did was break the square root of 10 into the square root of 5 times the square root of 2. Now when I simplify this first one, I'm going to get the square root of 25 times 2. Well, the square root of 25 is 5. So I can just bring down the square root of 2, and this would be my answer. Bit of a tip. Multiplying the square root by itself gets rid of the square root. Okay? So what happened is when I multiplied the square root of 5 times the square root of 5, the radical actually went away, and I just have 5. Because the square root of 5 times the square root of 5 is the square root of 25. Okay? Because of this rule, I don't have to do this middle step. I can go straight from seeing I have two of the same radical being multiplied to each other and just cancel out the radical. Let's do this next one. Same thing, I'm going to break all these up, and I have the square root of 2 times the square root of 3 times the square root of 4 times the square root of 2. Now immediately I notice that I have the square root of 4. So that is going to be equal to 2. The square root of 4 is 2. But looking at my red rule, the rule multiplying a radical by itself, I see I have the square root of 2 and another square root of 2. Therefore, when you multiply a radical by itself, the radical goes away. All right, the square root of 3 doesn't go any further than that, and it just comes straight down. Therefore, my answer is 4 times the square root of 3. Now, this rule works for variables as well. Now, depending on which class you were in, you either have the first one or the second one in your notes. I'm going to re-explain the first one, but then I'll show the answers for both. All right, now what you're going to do whenever you have these problems is you're going to take it one piece at a time. So I have the square root of 32. The square root of 32 can be rewritten as the square root of, we can go with 8 times 4. Okay, I like that because there's a perfect square in there. And I'm going to break down 8 even further, and now I have the square root of 4 times the square root of 2 times the square root of 4. Okay, now I notice that I have 2 square roots of 4, and whenever you multiply a square root by itself, the radical goes away. So the simplified answer will be 4 radical 2. Okay, because I multiplied those two things together, and the radical went away. Next, I have the square root of r squared. Now, by definition, the square root undoes the square, which means I'm just left with r. Next, I have k to the 4. Now, if by definition the square root undoes the square, then it'd be a good idea for me to look for squares. So how many squares are in K4? Well, there's 2. There's 1 square times the other one. Okay, because remember your exponent rules. When you multiply variables, you add the exponents. This is going to simplify. I'm going to get a k out of this first one and another k out of the second one, which means my answer will be k squared. Or you can look at it and say, I have a radical that is being multiplied by itself, which means the radical goes away. Last piece, I have t to the 5th. I'm looking for squares again. I know that if I have to the 4th, I have 2 squares, so t squared times t squared. But then I have one more number that needs to happen, so I'm going to put times t in the last one. Now again, a radical multiplied by itself cancels out the radical, so I have t squared on the outside, but the square root of t doesn't have anything, so it stays inside. So now I have all these wonderful pieces, but my answer needs to have all of them together. So I'm going to put all of them together, and I have 4r k squared t squared, the square root of 2t. And that would be my final answer. Okay, the video is going to pause, and then you'll see the answer for the next one. And there's the answer for the next one. Okay, remember, the process works no matter how many pieces you have, you just do it to one piece at a time. Now, I do want to draw your attention, before we change slides, to the order of the terms. It will always go number first, whether you're outside the radical or inside the radical. It will always go number first, and then the variables in alphabetical order. Okay, that's just how you set up your problem, or your answer in this case. Okay, now the quotient property of square roots. We talked about this beforehand, but whenever you have a fraction as the radicand, you take the square root of the numerator and the square root of the denominator. The only other thing I have to add to the slide is a reminder that b cannot be 0, because you can't have 0 in the denominator of a fraction. it won't work. Okay, let's practice. So in this one, we need to rationalize the denominator. Please know this phrase. I will use this constantly, and you will hear it constantly. You rationalize the denominator to eliminate the radical. So let's think. How can I eliminate the radical? What can I do to get rid of the radical? Well, if you've written it down, then you know that you can multiply a radical by itself to get rid of the radical. Okay? So we're going to multiply the denominator by itself, the square root of 12. But if you know the golden rule of fractions, you know whatever you do to the numerator, you must do to the denominator. Whatever you do to the denominator, you must do to the numerator. Therefore, we are going to multiply the top and the bottom by the denominator. So, we now have succeeded in getting the radical out of the denominator. And now we have 6 times the square root of y times the square root of 12 in our numerator. And I wrote it like that on purpose because, remember, we must simplify completely. And it's easier to simplify smaller numbers than it is to do bigger numbers. So, let's break down our numerator even further. I'm going to do 6, I'm going to leave 6, and then I'm going to do times square root of y, and I'm going to break up 12 into 6 times the square root of 2. A radical multiplied by itself is just the number. So I'm going to have 6, square root of y and the square root of 2 don't simplify any further, so 2 and y. And then my denominator is 12. My last step is that my numbers can simplify further, which means this will cancel, and I have the square root of 2 over 2y over 2. And that is the completed simplified fraction. Now, we won't always have monomials in the denominator. The last slide was a problem where the denominator only had one term in it. And even if you had a term times a variable, that's still a monomial. We will often have binomials in the denominator, so we need to know what to do with those. So let's think. Currently, what we need to do is we need to rationalize the denominator, which means we have to get the radical out of the denominator. However, if we do what we did the last slide and multiply the denominator by itself, here I have 5 plus the square root of 2 times 5 plus the square root of 2. I'm multiplying it by itself. 5 times 5 is 25 plus 5 root 25, 5 root 2 plus 5 root 2. A radical times itself is plus 4. This is how it simplifies. Now, if this confused you, it shouldn't, okay? What you can do is think about it in terms of x. So instead of a radical 2, let's do the exact same problem but have x instead. So I have 5 plus x times 5 plus x. Okay, it's the exact same problem. You can even compare down to the bottom. Okay, it's the exact same setup. The only difference is that, again, the square root times the square root is going to equal, math error, oops, the inside number, so not 4. Okay, but a square root times a square root is going to equal the inside number, and therefore it could be simplified one more time and give you a number plus a square root. Okay, but the main thing I want you to know about this, we'll do more of these styles of problems later, but the main thing I want you to see is that when we multiply the denominator by itself, we still had a radical term. This middle piece simplified into a radical term. And we're trying to get the radical out of the denominator. So we got to rethink this. What process gets rid of the middle term? Hopefully you were thinking that you change the sign, which would be correct. Okay? Now I'm going to do this with my blue equation up top, so you can see how this works without being confused by the radical. So let's say I had 5 plus x times 5 minus x. Okay, I changed my sign. Let's see what happens. I still get 25 as my first term. All right, then I get 5 minus 5x, and then I get plus 5x, and then I get minus x squared. Now my middle term cancels, and I am only left with the square of my first term minus the square of my last term. This is good, because once we have our square root term back, that means that this middle term, the radical term, will be eliminated, and will only be left with the square of the first term and the square of the last term. Okay, this is called the conjugate. The conjugate is when you change the sign of the denominator. So whenever you have a binomial, instead of multiplying the denominator by itself, you're going to multiply the denominator by the conjugate. That way we get rid of the whole middle term. And you can read it happening here. So we multiplied by 5 minus square root 2, 5 minus square root 2, which means you're just going, in the denominator, you're just squaring the first term and squaring the last term. Because as we proved over here, whenever you have different signs, the middle term will cancel. Okay? Meanwhile, don't forget you must distribute your numerator into the parentheses. So maintain those parentheses until you're all the way done. In our denominator, the square of the first is a bigger number, 25, and the square of the second is, whenever you square a radical, the radical goes away, so it's just 2. Okay? In the numerator, when you distribute, you get 15 minus 3 root 2. The numerator cannot be simplified any further, but the denominator can, and you get this as your answer. We'll do a few more of these in class. We have one on the next slide, but we'll do a few more of these in class so you can have the chance to ask me questions. Okay? The two things I want you to take away from the slide. Number 1, the definition of the conjugate. What does that mean? And why are we doing it? And that you have to distribute into the binomial. Okay? Let's practice. So here we go. We're going to multiply our denominator by the conjugate. So I'm going to do 3 plus the square root of 7 over 3 plus the square root of 7. I'm going to do my denominator first, that way I don't forget about it. Okay, so in the denominator, 3 times 3 is 9. Negative square root of 7 times square root 7 is negative 7, because a radical times itself is just the inside. And then I'm going to rewrite my numerator. Okay. If you need this denominator step explained, here it is down here. There it is with all the steps shown. Okay. If you have any questions about this, please make sure to ask me in class. Okay. Now, back to my original problem. Before I simplify my numerator, I'm going to continue my denominator. The reason for this is sometimes we can simplify if the denominator matches the numerator. In this case, it doesn't. 7 and 2 do not simplify, so now I can distribute my 7 into my numerator. And I have 21 plus 7 root 7 all over 2. This is my final answer. And that is the end of the PowerPoint. Now, I know this last section did have a lot of math going on. Okay? What I want you to do, go back and make sure you're really reading the math. Look at the steps. Follow it step by step. Okay? The main thing we're trying to do is get rid of that middle term that when we add it together normally would be a radical term. We want to get rid of that, so we have to change the signs. If you do have any questions, please make sure you ask me next time I see you, and I'll see you next time.